All right. So now we're going to go over some ways that we can characterize the various properties of powders. All right. So I've put together kind of a list of ones that I'm going to talk about. But again, keep in mind, these are not all the various ways that we can characterize powders. I'm just sort of giving an overview of some of the techniques, what they do, what they tell us, and obviously there's more out there that I'm not mentioning. So, some of these will tell us information about particle size. That's a big uh, need in powders, is to know what the particle size is. And so, microscopy, sieving, sedimentation, the Coulter counter, light scattering, X-ray diffraction, those are all kind of various ways in which we can get some information about particle size and so forth. BET is another method similar, but it tells us about surface area. And then some of these others tell us about composition. So, wet chemical techniques, this can tell us about composition. Same thing as flame emission or NMR and AAS. Okay, so the first technique that I want to talk about is microscopy. So I kind of lumped all of my microscopy together. So this could be light microscopy, so a simple light microscope. This could be SEM, scanning electron microscopy. This could be transmission electron microscopy, TEM. Any of those methods where we can directly observe powders. So we can get particle size, we can get morphology, so shape information as well. Some of these techniques will also give other information. So SEM, when equipped with energy dispersive spectroscopy, EDS, can give us composition information. And TEM can do the same with EDS or EELS, a technique called EELS. And it can also give some diffraction information as well, which is more complicated, but it can still do those techniques. So this, I'm just kind of joining all these kind of various microscopies together to sort of say this is one way we can directly observe particles. All right, sieving. So this is a very old and very simple technique, but it still has its merits. So just because it's old doesn't mean it's not useful. So this is one that was used in lab or would have been used in lab, and it's a way that we can sort particles by size. And so it's a way we can actually physically separate particles, and so that can be useful for various applications, but it can also be used as a characterization tool to see how much that we have in a given size range. And so these are examples of some sieves, and you can kind of see from the bigger ones that basically they just are meshes. They have basically metal wires that go in perpendicular directions, and so you have basically a square opening known as an aperture. So this table from a different book, you can also find a lot of this information online, but basically there will be a sieve number, and this is kind of a standard in the U.S. There's a U.S. sieve kind of standard, and so a given number, so for example 3.5, will correspond to a particular aperture opening. So you can see that this is a relatively low number, 3.5, and it has a relatively large aperture opening. So 5,660. And that's in microns. And so if you convert that, that's in millimeters, right? So basically 5.7 millimeters. So that's pretty big, right? So we're talking basically this size. And then the higher you go, you'll see that if we go up to 325, this is one of the ones that we used in lab or would have used in lab. That has an opening size of only 44 microns, so much smaller. So that kind of gives you the relationship between sieve number and the aperture opening. And so there's a series of these, and you can buy lots of different combinations. And the idea is that we can use these to sort a powder. And so the way we would do this is we would stack them. So we would stack these sieves with the smallest number on top, so the biggest opening, and then the smallest opening ones or largest number on the bottom. And so we would basically pour the powder in top. Anything that's smaller than the opening size would go through. that opening, and etc. until we get to the bottom. And so anything that's on, for example, anything that doesn't go through the opening is larger than that aperture size, or just at that size, right? So it can't go through quite. And so that would tell you the range in which you have particle sizes, right? So for example, if this first one was 3.5, it would say that whatever mass I have above that sieve is going to be larger than 5.7 millimeters, right? And so you can basically characterize, I have X amount, so I have some mass above that, some mass in between these two, some other mass in between. And so it'll give you a percent, a weight percent between each variety. And so you can see here that there's quite a wide variety. This very fine powder down here, a slightly coarser, these sort of pebbles, and then progressively larger and larger sizes. And so that's what we can do. We can sort them, and it's a very easy, quick way in which we can do this, and also separates. So there's an additional benefit beyond the characterization that sieving does for us. Okay, another method we can use to determine size is known as sedimentation. And I put this in here because it's a quite simple method in which to determine particle size. But as you can kind of see from the vials here and in the name, is basically what we're doing is we're putting a powder in a liquid. We're going to make sure it's homogeneous. So basically you formed a slurry. It's not a solution because the particles are not dissolved. They're just homogeneous. They're still distinct from the liquid. But if they're not stabilized in any way, eventually they will fall to the bottom, or sediment to the bottom. And so you'll see it growing here. So this one has some sediment on the bottom, more, and more that reaches the bottom, right? And so the velocity at which it falls through the liquid can be used to determine the particle size. So the easiest way is if we have a homogeneous particle size. So all the particles are the same size. This is basically some of the limitations to this method. And so we can use Stokes Law, which tells us about the force acting on a particle in a liquid, and therefore can give us the velocity and tell us how long it's going to take to reach the bottom of the vial. So if we just sort of go through this, there's going to be a frictional force on the particle in a liquid. So that's F here. And it's going to be a function of the viscosity of the liquid. So this is something that we could vary. We could do water, we could do oils. There's various liquids that we could use. And then it's also going to be a function of the particle size. That's what's useful for determining particle size. And then, excuse me, and then it's going to fall at a given velocity. So this is Stokes' Law. So maybe you've seen this in other classes, but this can allow us to solve for the radius. And so the way we do that is actually to look at the velocity, right? So imagine you are kind of doing this experiment. You've got a test tube here, and you have a given test tube. It's got a certain height to it, and so particles have to fall a given amount. And so you can record the time it takes to do that, and that converts to a velocity, and you can get the radius from that using this equation, which is another variation of Stokes' Law, using the differences in the densities of the particle and liquid, the gravitational constant, and again, the viscosity of the liquid. So this is useful for a somewhat narrow range of particle sizes, so about 1 to 25 microns. So it works well within this range. So it's somewhat limited, but it is a useful and simple way if applicable. Excuse me. Okay, so I want you to sort of think about an example of this. And so here I'm asking you to calculate the sedimentation rate, so a velocity, for spherical particles of alumina in water at room temperature. And what I'm having you do is kind of test the bounds of the size range. So imagine we have a radius of 1 micron and a radius of 25 microns. So see how long, so see if you can approximate how long it would take for the particle to reach the bottom of a vial. So what I'm going to have you do is make some approximations. So you're going to have to kind of assume how long the vial is, and then it's asking for densities here and viscosity of the liquid. And so these are things that, since you're kind of at home in front of your computer, I'll have you look up. So look up the densities of those materials, viscosity of the fluid, and then see if you can calculate the sedimentation rate of this. So pause, see if you can kind of track down those numbers and do this quick calculation, and then approximate how long it will take for that particle to reach the bottom of the vial. And then we'll come back, I'll show you the numbers I've got, and we'll go walk through this calculation. All right, so we're back, and let's see if we can calculate the sedimentation rate for these alumina particles in water at room temperature. All right, so I've got kind of my worksheet and how I calculated this. So the first thing up at the top, you'll kind of just look and these are the values that I came up with from various sources online. So I got the density of Al2O3 alumina. So I've got that in grams per centimeters. I've also got it in kilograms per meter. Same thing for water. So 1,000 kilograms per meter. Again, all of this kind of at room temperature, or as close as you can find. The viscosity, same thing, you'll want it at room temperature. It can vary. So this is the viscosity of water at room temperature. So this is in Pascal seconds. The first thing is I've got everything sort of in SI units. I've converted to kilogram meters, Pascal seconds, and then I've also got the gravitational constant in meters per second, and then a radius in meters as well. So I've changed everything into SI units. And so then if I look at the velocity equation, I'm plugging in the velocity of the solid minus the liquid, and then gravitational constant, and then the radius squared, and then over 9 times the viscosity. And so when I do that, I get a velocity of 7.23 times 10 to the minus 6 meters per second for the small particle, and then 4.52 times 10 to the minus 3 meters per second if I'm looking at the 25 micron particle. So same calculation, I just changed that one number. All right, so I've got the velocity, which is the first part of the question that I was asking. And so for the second part, I was asking for how much time, right? Because if you're actually doing this experiment, you're not directly measuring the velocity, you're measuring the time it takes to reach the bottom. And so here, what I'm going to do is I'm going to assume that the velocity is constant throughout over the vial height, and I'm assuming a vial height of 15 centimeters. So this is, roughly the height of a vial in the lab. But again, if you made a different approximation, that's fine. This is just to get some rough numbers for how much we think it would take. All right, so if I do that, then my time becomes, or the velocity would in effect be height over time, so distance over time for constant velocity. So if I rearrange that to solve for time, for the 1 micron particle, I would have the height over velocity to get units of seconds, and so that would give me over 20,000 seconds. Those aren't the greatest units to kind of see what this is. So that's 346 minutes, or basically 5.8 hours. So these very small particles take a long time to fall that 15 centimeters is basically what this is saying. Okay, so then if I go to the next one, I take the velocity for the 25 micron particle, do the same thing, same 15 centimeter height, use the different velocity, sorry. Then I get, in units of seconds, 33 seconds. So I didn't change the units here, but this should be 25, 25, and 25. So all of these, the height is the same, but the velocity is for the 25 and the time is for the 25. So the 25 micron particle only takes 33 seconds, right? So from this, generally speaking, Stokes' law will tell us that larger particles fall faster, right? So that probably sounds familiar just from common knowledge, but that's what Stokes' law tells us. And it can give us the velocity. We can calculate the velocity or measure it, and then compare that to what we have. And so that way, if we measured a time it took to fall the distance of the vial of 33 seconds, then that would tell us that we have a very small, close to 25 micron particle. And then if it took closer to 6 hours, then we would know that we have 25 micron particles, right? So that time it takes tells us the size of the particle. So that's the way we can kind of do that calculation. Okay, so let's move on to the next type of measurement. And so this is a Coulter counter. And so this is, again, another way we can get particle size. So I'm kind of stressing this particle size because, again, this is one of the common measurements that we're going to make, but there are limitations and advantages to certain methods and certain types of particles that work better. And so that's why we kind of need so many different methods. So in this case, we measure particle size in an electrochemical cell. Excuse me. So basically what we have is we have two electrodes. So our system here has an electrode inside this vial. We have another electrode in this solution out here. And so within this vial, there is a small opening known as an aperture. So again, just a small opening in this material. And so our particles are within this sort of vial here that has an aperture opening into it. And then we have those two electrodes. And there's an electrolyte in all of this solution. So what it does is it measures particle size by actually looking at the changes in the electrochemical cell with the change in electrolyte. So if you can kind of imagine, every time a particle goes outside of this aperture, so it moves from this vial, goes through the aperture into this larger solution, an equivalent amount of electrolyte would have to go the opposite way into this vial to take its place, right? So an equivalent volume of electrolyte flows in the opposite direction. And so that difference in electrolyte is what we measure. So we're basically measuring a change in resistance because there's a change in the electrolyte composition between this small area and this area out here. So we're measuring that change in resistance, equating that to the volume, and then that can tell us the particle size because that displacement is proportional to the change in resistance, which is proportional to the change in particle size. And so that's how we get this. And so what that might actually look like. So again, we have this aperture opening, a particle goes through, we have that change in resistance. Excuse me. And that's kind of converted into these voltage pulses, which can be used to give us particle size. So basically, excuse me, this differential volume here equates to 0.8 microns. This one closer to 0.5 over here. And so it can give us a distribution plot of the various sizes that we have in this material. Okay, so the next one that I want to talk about in terms of particle size is another pretty common technique for measuring particle size, and it's again a slurry-based approach. Excuse me. So in this case, we use helium neon laser. So we have a laser beam directed at particles in a solution. And the way that the laser beam interacts with the particle causes scattering, so light scattering. And so it scatters by a certain angle theta. And so that theta angle is proportional to the diameter by this equation over here. So the sine of the angle theta is equal to 1.22 times the wavelength of the laser. So for this helium neon laser, it's 0.63 microns, and then divided by the diameter. So what that does is we can basically detect this this scattering, and we can equate that to a size. So here, so that was kind of a large, quote unquote, large particle. Here, this is a quote unquote small particle. And so the same beam interacting with that smaller particle actually scatters to a higher degree. And so this scatters more, has a higher angle theta, and again can be equated to the diameter. And so this all sort of goes back to interaction with small particles with respect to various wavelengths. And so when the wavelength, when the particle approaches the wavelength of the light, then the scattering is more and more. And so we use that principle, that light scattering principle, to determine the particle size. So again, all of these methods have their own advantages, disadvantages. This is a very quick method. And then the reliable range in which we can cover is about 2 to 100 microns. And so it's in that micron range that we can detect. So you're seeing some limitations of some of these methods if you have really small particles on the micron or on the nanometer scale, or really large ones. Okay, so we'll come back and look at some of the other characterization techniques.